Okay, I've just opened RStudio on my computer, and the first thing I'm going to do is move to the directory where I have the code. So this will be different on your computer. And once that's there, you can open up the files. I already have it open here, but you would just click on Open File, and you'll open this one, Simple Linear Regression. All right, so the goal for this demonstration is to put what we've been learning in the lecture into practice by analyzing a data set. The particular data set we're going to analyze is inside of the textbook's R package. So the textbook has an R package called ALR4. So the first thing you'll need to do, I've already done this on my computer, but you'll need to run this line to install the textbook's package. And that will take a minute or so. And then you have to attach the package to the workspace. And so the way you attach a package is with the library command. So just run that, and it spits out some information. And R packages are, it's a set of code that someone has written that they want to share with someone. In many R package, in addition to code, they include data sets. So the way you load in a data set from an attached package is you have to know what the data set is called. But I know that there's a data set called heights in the ALR4 package. So if I run this, I will have a data set called heights. So if I run this line, it will print out the data. The first thing I want to do, though, is to look at the documentation for the heights data set. So if I do $heights, it will pull up a little window here that has some information about the data set. So this is a data set from 1,100 families in England in the late 1800s, and it has the heights in inches of mothers and their daughters, and up to 2 daughters per mother. All the daughters are at least age 18, and all the mothers are younger than 65. The original data were given to the nearest inch, but this particular data set, they've added essentially random error so that the data are reported to the nearest tenth of an inch. That's just to help with plotting. Okay, so there's several ways to look at data sets. One convenient one is to do head of the data set. So right now there's an object called heights in the workspace. If you type it in, it will print out some of the data. If you want to just look at the first few rows, you type head of height. This will print out the first 6 rows. And you can see that there's one column M height for the mother's height and one column D height for the daughter's height. If there's any ambiguity about what the columns are, often in the documentation for the data, they'll tell you what they are. Okay, there's other things you can extract from the data set. Names, heights, these are the names of the columns. N row is the number of rows in the data set. So here in the documentation it said there's 1,100 families, and some of the families have 2 daughters. So that's why there are more than 1,100 rows in the data set. STR of heights will print out some information about them. It says that heights is a data frame. It has 1,375 observations, and this is just an example of some of the values. On top of that, I'm going to define my own variables called M height and D height. If you want to access one of the columns from the heights object, you do heights $M height. I'm going to get tired of typing up heights $M height every time, so I'm going to define a variable called MHT for mother height and DHT for daughter height. All right, the first thing I want to do here is to plot the data. So in the plot command, the first argument is the variable that goes on the x-axis. Second argument is the variable that goes on the y-axis. And then there's lots of additional arguments you can supply. I'm just going to supply a label for the x-axis and a label for the y-axis, and then let the plot function choose all the default choices for everything else. So that's a plot of the data, and I'll just add a title to it with the title command. And so here you can see a scatter plot of the data. I didn't quite like this plot, so one sort of general rule of thumb is the more points you have in a plot, the smaller you should make the plotting symbols. If you want to make the plotting symbols smaller, you can add an argument to the plot function called CEX that changes the size of the plotting symbols. If you do CEX equals 1, that is the default, and then anything smaller will scale them smaller, anything bigger than 1, like 2, will make the plotting symbols bigger. So I found 0.3 gave a nice looking plot. Okay, so I think this looks a little bit better to me. Now that we have a plot of the data, the next thing I want to do is compute some summary statistics. There are several ways of doing this. One of them is to use the summary command. So we do summary mother height and summary daughter height. That will spit out a 5-number summary. Actually, this is 6-number summary. Minimum, first quartile, median, mean, third quartile, the maximum. So if you look at these summary statistics for mother's height and daughter's height, you'll see that they're pretty similar. Another thing you can do is just define your own summary statistics. So what I'm doing in these two lines is I'm using the C function, which is the function for creating vectors. So for example, I could do C 5.6, 8, 3.2, 10, and that will create a vector with those values in it. You can also, with the C function, you can also give names to the values. So you can say B equals 3, C equals 4, and that will give names to the variables in the vector. So here I'm defining variable mom average as the mean of M height, mom SD as standard deviation of M height, and the same thing for daughters. So this spits out the means and the standard deviations, which again are pretty similar. All right, now I want to actually figure out or do some inferences about what the relationship between mother's height and daughter's height is. So if you look at the scatter plot, you can see that there is some relationship, but there is a lot of variation. Even if you knew the mother's height was 60, the daughter's height could be as low as 58 up to 68, for example. So there does seem to be a relationship, but there's a lot of variation around it. So now I want to do the regression calculations to get some estimates and make some inferences about that relationship. So I'm going to define X as mother's height. That's going to be my covariate. Y as the daughter's height. So that's my response. N is the number of observations, which is equal to the length of X. X bar is mean of X. Y bar is the mean of Y. SXX just has this definition. You take X minus X bar. Those are the numbers, X minus X bar. You square all those values, and then you add them up with the sum function. And then SXY is similar, but you have instead of X minus X bar squared, you have X minus X bar times Y minus Y bar. So that's that. And then we have a simple formula for B1 hat, which is just SXY over SXX. And the formula for B0 hat is Y bar minus B1 hat minus X bar. Okay, so B1 hat, the estimate of the slope is 0.54. What this means is that if you increase your mother's height, which is not possible in practice, but if you had two observations where one of the mothers was 1 inch taller than the other mother, then you expect the daughter with the taller mother to be 0.54 inches taller. So this is less than 1. The residuals are defined as just the response minus the predicted values, so b0 hat so y minus b0 hat plus b1 hat x. And then you can calculate the estimate of sigma by using the residual sum of squares. So this is the residuals, they're squaring them, and then this is the sum. And then you divide that by n minus 2 because the linear model has 2 model degrees of freedom. So this is sigma hat. Sigma hat is 2.26. So what that means is that the expected value for daughter height is b0 hat plus b1 hat, but you also expect the daughter's height to deviate from that expected height by roughly 2.26 inches. All right, one of the quantities we talked about computing is r squared. So this is the residual sum of squares divided by SYY. And in this case, r squared is 0.24. So the interpretation of that is that 24% of the variation in daughter height can be explained by mother height. So it's not an extremely strong relationship. Okay, and then these are just calculations of the standard errors for B0 and B1, just using the formulas that we talked about in class. All right, the standard errors are the following. So this is standard error of B0, B0 hat. So the estimate of B0 hat is 29.9. This is not a particularly interpretable number. What this means is that it's the expected value of daughter's height when mother's height is 0, which won't ever happen in practice. So we shouldn't pay too much to the particular value that B0 is. The more interpretable one is B1 hat, which, like we said, was 0.54. And then the standard error of B1 is 0.0259. So we have estimates of B0 and B1, and it seems pretty clear that there is a relationship between them. But just to be sure, we should do a t-test of the hypothesis that B1 is 0. Okay. So if you want to, the first thing I'm going to do is figure out what the cutoff needs to be in order to do this t-test. So null hypothesis B1 equals 0. Our decision rule is that we reject it if the absolute value of the t-statistic, which equals B1 minus 0 over the standard error, is big enough. And so we have to define what big enough is. And the false positive probability we're going to use is 0.01. So if you want to calculate what that cutoff is, you can use the quantile function of the t-distribution. So what this tells us is how far out we have to go into the tail of the t-distribution so that the probability of being larger than a particular value is equal to 0.005, which is our alpha divided by 2. The reason we divide by 2 is because we're using the absolute value of the t-statistic to determine our test. So we will reject if t is large, so bigger than the value that's returned here, or we'll reject if the value is small, so less than the negative of this value here. Okay, so this returns this quantile. It returns the left quantile, so it's minus 2.57. The t-distribution is symmetric, so if you want the right quantile, you could just do the absolute value. So this is our cutoff. You get the same answer, so this would be which value of t has 0.005 to the left of it. This means which value of the t-distribution has 0.995 to the left of it, which means 0.005 to the right of it. So this is 2.57. if you want to verify that this is right, I mean, R will give you the right answer here. But you can use the PT function. So the PT function calculates the probability of getting value in the t-distribution less than a particular value, the cutoff. So this tells us the probability of getting a value on the t-distribution less than cut, and we're going to look at the lower tail. So this would be less than, this gives us less than minus cut, and then this is the same thing. So if you add these up, you get alpha, which is 0.01. The t-statistics we observe are just b, let's focus on this one. So this would be b1 hat minus 0, which is the null hypothesized value of b1, divided by its standard error. So that's t1. And if you ever get a t-statistic of 20, you're going to reject the null hypothesis. But just for fun, so 20 is bigger than our cutoff, so we're going to reject. And let's also compute the p-value. So the p-value, you plug in the statistic to figure out what the probability is of getting something more extreme than the statistic you observed. So the p-value we get is 3 times 10 to the minus 84. So this will tell us we put lower tail equals false here. So this gives us the probability of getting something larger than the T1 we observed. And if you do lower tail equals true, this is the probability of getting something smaller than the minus the statistic you observed. So you're calculating the probability in both the left and the right tail, because our decision rule was to reject if the absolute value is large. Okay, so we've done a t-test for whether the slope b1 is equal to 0, and we did everything by hand using the formulas we learned about in class. That can get a bit tedious, but fortunately R has commands that does all of this for you. And the workhorse command that we're going to be using this semester is called LM. So LM is a function that fits linear models. So it'll fit the simple linear models that we've talked about in class, and also multiple linear models that we'll get to next week. So the way the LM command works is the first argument is what's called a model formula. And the way the model formula works is you put the response first, and then you do tilde covariate. So this is response tilde covariate. When we start to add more variables in multiple linear regression, you add covariates on this side. So if we had dad height, we could add that here. But we're just doing one variable right now. If you specify variables here, you can also specify what data frame they're inside. So we have a data frame heights, as you recall. It has m height and d height in it. Now m height and d height are not in the workspace themselves. M height says error, m height not found. D height is also not in the workspace, but it is inside of this heights object. So you can specify your models like this with variables inside of a data frame, but then you have to tell LM which data frame you're talking about. So if you do this, it'll fit the linear model for you. It's the same thing since we defined DHT to be equal to heights dollar D height and MHT to be heights dollar M height. This will give you the same exact thing. Okay, so the summary function will give you the results. So M1 is the object that we stored are the results of the LM command in. So if we do summary M1, it'll print out a bunch of stuff. This is the line of code we use to fit the model. So this is the call to the LM function. These are some summary statistics for the residuals. And then the main thing here is a table of coefficients. So this model just has two coefficients in the mean part of the model. Intercept is the estimate of B0, so B0 hat, this should be the same, 29.91744. This is the one we calculated by hand. And then 0.54175, as you recall, is equal to the one we calculated by hand. These are the standard errors, so it does all these calculations for you. Remember SEB0 we calculated, SEB1, those are the same. And then the T statistics. There's T1, so this should be the same as this one. And it calculates p-values for you. It didn't print out 3 times 10 to the minus 84, it just says it's less than something really small. There's also some additional information. This is sigma hat, residual standard error. This is residual degrees of freedom. This we'll talk about later. And it does F statistic, which we'll also talk about later. So the main things for now are all in this table here. There's also a bunch of other stuff inside of this LM command. So if we do names M1, this will show all of the variables that are inside of this M1 object. And you can access any of them by doing M1 $. Let's do call. This is the call to the function we used. M1 $, residuals. Those are the residual values. And there's several other things. So M1 $df dot residual. This should be 1373. So this is n minus 2. If you want just the coefficient values, so this is B0 and B1 hat, which is the same as this. The summary function also has a bunch of information in it. So summary M1 is a call to a function, but it returns an object, and that object has a bunch of different things inside of it. So in particular, if you want to get the sigma hat out of the fit, you have to get it from summary. So summary M1 $sigma is that value, which is, again, the same thing that we calculated. Also, the R squared is in here as well. If you want the table, if you want to pull out those values, it's in the summary command. So that has summary, the table. In particular, you can do summary M1 $, and then you can pull out individual entries from this table. So this would be B1 hat. Okay. Now that we have our fits, we can add a trend line to our plot. So this is the same plot that we had before. If you want to add lines to a plot, one way of doing it is with the abline function. So the abline function takes 2 arguments. The first is a intercept, and the second is a slope. And then you can also specify other options. So I want to make the color of this line blue, and I want to make it thicker than the default. So I made it 2 instead of 1. So this puts a blue line. So this is our estimated linear relationship between mother's height and daughter's height. You can learn more about the abline function by doing question mark to pull up the documentation. One interesting thing is if you do abline of M1, which is a output from a linear model fit, it knows how to extract the coefficients and put them in the right arguments to abline. Okay, when we did the t-test for whether B1 is 0, we got a p-value that was extremely small, like 3 times 10 to the minus 84. So that means that there's very strong evidence that B1 is not 0. As we ended class today, we shouldn't confuse that with saying that the relationship between mother's height and daughter's height is very strong. There's other measures that we can use to assess the strength of that relationship. So p-values are a measure of the evidence against a particular null hypothesis. So one thing we mentioned in class is that when the null hypothesis is true, the p-value should be a uniform random variable viewed as when you view the p-value as a random variable. And this should be true regardless of the sample size. So the first thing I'm going to do is just a little simulation with several different values of the sample size, where we're going to simulate data assuming there's no relationship between mother's height and daughter's height. So we're going to simulate data that has a constant line across here. And then we're going to do a test using the simulated data of whether the null hypothesis of B1 equals 0 is true, compute a p-value, and then collect all those p-values for a bunch of different sample sizes. So this will hold the different sample sizes that we're going to use. We're going to use 10 up to 1,000. This will hold the p-values that we calculate for each simulation. B0 we're going to set to be the mean of mother's height, and then we're going to set B1 equals to 0. So this is a simulation. We're controlling the model. We're going to simulate from the model, and we're going to see how the statistics we calculate behave as a result. So let me just show you an example. So let's set J equal to 100. So we do n-vec of J. This will be 109. We're going to take a subset of length 109 of the mother's heights and call that x. So these are 109 mother height values. And then we're going to simulate responses y. So we're going to simulate from the model formula. So B0, which is equal to the mean of mother's height, plus B1 times x, and this is 0 in this simulation according to this line. And then we're going to add error to it. So if you want to add error that has standard deviation sigma hat, you simulate normals with variance 1 and multiply that by sigma hat. So here, let me plot. These are our simulated data that has no relationship between mother's height and daughter's height. You fit a model, and then you extract the p-value for B1 and store that in the jth entry of p-valvec. So this does the same thing for n equals 10 up to n equals 1,000, storing all of them. And then we can make plots of these p-values. So these are two plots. These are the p-values we got as a function of n. So these are sort of, if you look at the y-axis, they're scattered between 0 and 1. Taking the same thing and just plotting them as a histogram, you can see that this is pretty uniform distribution on 0 to 1. And this is exactly what we expect, because in this case, we simulated data under the true null hypothesis. So you should get p-values that are uniform. Okay, now we're going to do the same thing, except we're going to simulate data assuming there is a relationship between mother's and daughter's height. This time we'll do n from 10 up to 1375, which is the 1375 is the largest value of n that we had. This stores the p-values. This stores the estimates of B1 that we get, which we didn't store before. This stores the r-squared values. And I'm going to set B0 to be the estimated value from the model we fit to the real data. So B0 and B1 are the estimated values from Pearson's height data. And then the rest of this is all the same. We're going to extract the n, extract some mother's heights, simulate data. So here B0 is the estimated intercept for the Pearson data. B1 is the estimated slope for the Pearson data. Fit a model and extract the p-value, the r-squared value, and the estimate of B1. So let's run all that. And now if we plot p-value as a function of n, the p-values are not near 0 when n is small. So what this means is that when n is small, there's not enough data to claim that we have evidence against b1 equals 0. But once the n gets above 100 or so, we do have enough evidence to reject the hypothesis that beta 1 equals 0. So you can see that the p-value is more a function of the sample size than the strength of the relationship, because the strength of the relationship was the same in all of these simulated data sets. Now this other thing are these other two measures. So what I'm going to plot here is r squared as a function of n. I'm going to plug in the sort of the true r squared value, and I'm going to plot b1 hat as a function of n. So recall that for each of these simulated data sets, we extracted r squared value here, and we extracted the estimated estimate of b1. And so you can see that as the sample size gets larger and larger, the estimates tend to center more on the true values, so here and here. So more data gives you more evidence against null hypotheses that aren't true, and more data gives you sharper estimates of the things that you're trying to estimate. The last thing I want to show is so r squared was one of the measures of strength of the relationship, and we got r squared about 0.24, which is sort of a moderately but not super strong relationship. The other measure of relationship between variables that we talked about were predictions and prediction intervals. So what I want to do here is use the fitted model and calculate prediction interval for daughter's height given particular values of mother's height. The two values of mother's height we're going to use just for demonstration are 60 inches and 66 inches. Expected value of daughter's height for these two mother's heights, we'll just plug in b0 hat plus b1 hat times x01, which was 60, and do the same thing for x02. So these are the estimated expected daughter's heights for these two mother's heights. So EY01, if you have a mother of height 60, you can expect the daughter to be height 62. EY02, if you have a mother of height 65, you expect the daughter's height to be, mother's height 66, you expect the daughter's height to be 65. Those are the estimated relationships under this model. And here I'm going to compute the standard errors for those estimated daughter's heights. So this is the formula we talked about at the very end of class today. So SEY01, 2.268, SEY02 is 2.269. So these are very close to each other. And then what I'm going to plot is I'm going to make a scatter plot. So let's start with that. This is the scatter plot of the data. I'm going to add to the data the predicted values for these two. Let me just make the plot first. The predicted values for these two mother's heights. So what I have here in red here is the expected daughter's height for a mother of height 60. Remember that was about 62. And what I have here is the expected daughter's height, which is about 65 point something when the mother's height was 66. And then the magenta lines here represent two standard errors above and below those expected heights. So one thing that's useful here is that you can see the sort of the range of values you expect to get for two different choices of the mother's height. And you can see that this distribution is higher than this one, but there's still quite a bit of overlap. So I think this is one sort of useful measure for thinking about how much information about daughter's height is contained in the mother's height. That you expect this daughter to be taller, but it's reasonably likely that this one would be taller than this one.